This is a somewhat formal look at rules of limits. Try not to be too intimidated. There's a few basic facts we're going to get from this lesson. But here we go. If the limit as x approaches a of f of x and the limit as x approaches a of g of x exists, they both exist, and we're going to let k be a constant. If that is the case, then here are some rules that we can use. The limit as x approaches a of f of x plus g of x is just the limit as x approaches a of f plus the limit as x approaches a of g. So the limit of the sum is the sum of the limits. So the way we can look at that is if I had a situation like this, where I was going to say the limit as x approaches 5 of x squared plus 3x plus 2. We would say the limit of the sum is the sum of the limits. So that would just be the limit as x approaches 5 of x squared plus the limit as x approaches 5 of 3x plus the limit as x approaches 5 of 2, whatever that means. As we look at our intro stuff, we can figure that out, but formally, that's our basic idea. The limit of the sum is the sum of the limits. Similarly, the limit of the difference is the difference of the limits. So no surprise if I gave you something like this, and I said the limit as x goes to 4 of the square root of x minus 5x, you would say that's the limit as x goes to 4 of the square root of x minus the limit as x goes to 4 of 5x, whatever that's going to be. All right, similarly, in a similar vein, next up we have the limit of f times g is just the limit of f times the limit of g. So what would that look like? Well, we could say something like this. We could say the limit as x approaches pi over 4 of x squared sine x. What would that would just be the limit as x goes to pi over 4 of x squared times the limit as x goes to pi over 4 of sine x. So that works for us. We want to assume these limits exist, as we said, for this to make sense. And they do in that case. Next up, we have the limit of f divided by g is the limit as x approaches a of f divided by the limit as x approaches a of g. So again, similar kind of thing as the last one we did. If I want the limit as x approaches pi over 4 of 2x over sine x, I would say that's the limit as x approaches pi over 4 of 2x over the limit as x approaches pi over 4 of sine x. And that limit does exist. Of course, you can't divide by 0, so you need to make sure that what you have here is not a division by 0 kind of thing. But again, basic rules: limit of the sum, limit of the difference, limit of the product, limit of the quotient behave exactly the way you'd want them to behave. So it's a nice, friendly mathematical concept here for us to work with. And we go on. Our next rule is the limit as x goes to a of some constant times f of x is that constant times the limit. So if I want to know what is the limit as x goes to 3 of 2x squared, well, what I can do is I could just say, well, the 2 comes out in front. That's 2, that's the constant, 2 times the limit as x goes to a of x squared, whatever that's going to be. So that is that idea. Next up, we have the limit of f of x to the n is just that limit raised to that n power, where n is a positive integer. So let's stick with our sine example. If I want the limit as x goes to pi over 4 of sine of x to the third power, what that would mean is, okay, you take the limit of that sine x and raise that limit to the third power. So limit as x goes to pi over 4 of sine x, take that limit and raise that to the third power. Next, we have same thing with square roots. Limit as x goes to a of the nth root of f of x is just behaving that same way. So what would an example of that be? Well, we could do something like this. We could take the limit as x goes to 2 of the square root. Well, I don't know, x squared plus 5x plus 1. So that is just the square root of that limit as x goes to 2 of x squared plus 5x plus 1. We got to be careful with this, though, because you know you can't take a square root of a negative number. So providing that the limits exist here, provided that limits exists, provided that limit exists, that rule is going to be one that we can use. All right, now we get some big ones. The limit as x approaches a of a constant is a constant. Now, I'd like to look at Desmos for that for a minute, if I can. I have to have it loaded. Doesn't look like I have it loaded here, so I will go ahead and load Desmos now. Struggling here. Here we go, Desmos. And I'm going to go ahead and pull that up. So I want to take a look at a constant like the number 7, f of x equals 7. As I approach any number, so let's say I'm approaching 2. The y values are always approaching 7. You see that? 2 from the right, the y values are always 7. 2 from the left, the y values are always 7. So as I approach 2, the function approaches 7. As I approach -6, y values are 7, y values are 7. As I approach -6 from the left, y values closing in on 7. As I approach -6 from the right, y values are closing in on 7. Anything I choose, 4, y values are 7. So if I'm approaching anything with a constant, right, the limit as x approaches a of a constant is going to be a constant. So I don't care what I choose. The example I just showed you, right? The limit as x approaches a of anything. I don't care which number you use. The limit as x approaches -1000 of 7 is still 7, right? That doesn't change. That's there for us. Next up, we have the limit as x approaches a of x is x. So let's think about that one. Let's go back to Desmos there as well. As limit as x approaches a number of x. So the example I'm going to look at here is, what is the limit as x approaches 3 of x? And that's not correct. The limit as x approaches a of x is not x. Limit as x approaches a of x should be a, and I'll show you in a minute why that's the case. So let's go ahead and look at that. Limit as x approaches a of x. Going to Desmos. The function I'm looking at is f of x equals x. As I approach 3, as x approaches 3, the y values approach 3 from the left. As x values approach 3 from the right, the y values approach 3. So the limit as x approaches 3 of x is just going to be 3. Similarly, how about the limit as x approaches -2 of x? Limit as x approaches -2 of x. Go back to Desmos. As I approach -2 from the left, y value is getting closer and closer to -2. As I approach -2 from the right, y value is getting closer and closer to -2. So indeed, that is the case. So limit as x approaches a number of x just equals that number, right? These have to match. Hence a there, a there. And all of this is getting us ready really for our last rule, which is that if we have a polynomial, the limit as x approaches a of the polynomial is just that polynomial evaluated at a. So the example we can look at there, if I give you a polynomial, and this is what I think of sometimes as the plug-in rule. You just plug in the number and see what happens, or the substitution rule. So if I have the limit as x approaches 2 of x squared plus 3x plus 1. Well, x squared plus 3x plus 1 is a polynomial. So I can just plug that in. And I can say, fine, plugging that in, I get 2 squared plus 3 times 2 plus 1, which is 4, plus 6 plus 1, which is 11. Which behaves the way we want it to behave, which is 11, not 1. And we can quickly take a look at that on Desmos if you'd like. So the function there is, again, x squared plus 3x plus 1. And we are getting closer and closer to 2 x squared plus 3x plus 1, getting closer and closer to 2, where the y value is getting closer and closer to, you can see indeed, as x gets closer and closer to 2, y values get closer and closer to 11 from the left and the right. So those are our basic rules. We have 10 of them. We keep them straight so that if I have a situation like this, if I'm told that the limit as x approaches 3 of f of x equals -2, and the limit as x approaches 3 of g of x is 5, and I want to know what is the limit as x approaches 3 of 4 times f of x divided by the square root of g of x plus 1. Essentially, all these rules tell me, right? The limit of the quotient is the quotient of the limits. So I could take limit as x goes to 3 of 4 times f of x divided by the limit as x goes to 3 of the square root of g of x plus 1. Then we had the other rule that said we can pull the constant out, so the 4 comes out. So that would be 4 times the limit as x goes to 3 of f of x divided by, we said that if we have the limit of the square root of something, that's the square root of the limit of the something, square root of the limit as x goes to 3 of g of x plus 1, which is, again, 4 times the limit as x goes to 3 of f of x equals, again, I have the limit of g of x plus 1. The limit of the sum is the sum of the limits. So square root of the limit as x goes to 3 of g of x plus the limit as x goes to 3 of 1. Well, what do we know? The limit as x goes to 3 of f of x up top was -2, so we get 4 times -2. Downstairs I have the square root. The limit as x goes to 3 of g of x was 5. The limit as x goes to 3 of 1, the limit of the constant is that constant. Visualize that horizontal line. As I get closer and closer to 3, it's just 1. I get 4 times -2 upstairs is -8. Root 5 plus 1 is root 6. So -8 over root 6, a perfectly good answer. In calculus, we tend to prefer square roots in the bottom to rationalize the denominator, so do not feel compelled to make that change as you go along. But keep in mind, the main idea of this lesson is to evaluate easy limits. Really, all you've got to do is plug it in. If you've got a polynomial, you can find the limit of a polynomial by plugging in that value.